This presentation is part of the TI in Focus AP Calculus video series. In this video, I'll discuss the solutions, relevant concepts, and the scoring guidelines associated with some of the parts of our 2020 mock AP Calculus exam, Form AB, Question 2. My name is Steve Kokoska. I'm a recently retired professor from Bloomsburg University in Pennsylvania, and I'm a former AP Calculus chief reader. Form AB Question 2 involves a particle moving along the y-axis. Its position is modeled by a twice differentiable function y of t, where t is measured in seconds and y of t is measured in meters. We're also given a table of values of y prime of t for selected values of t. And we also know that the position of the particle at time t equals 12 is minus 3. In Part E, we need to use a midpoint Riemann sum and 3 subintervals of equal length to approximate this definite integral. The key concept needed here is the definition of and the use of a Riemann sum, specifically a midpoint Riemann sum. Let me start with a very general definition, consider a few common Riemann sums, look at a typical application, and then finally solve our problem. Suppose f is a continuous function on the interval a to b. Let's divide the interval a to b into n non-overlapping subintervals, as defined by or specified by this list of values, where a is equal to x sub 0 and b is equal to x sub n. This is called a partition of the interval a to b, and it's often denoted in this manner. Let delta x sub I be the length of the ith subinterval, so delta x sub I is equal to this difference. And let x sub I star be an arbitrary value in the ith subinterval. A Riemann sum of the function f over the interval a to b with partition p is given by this summation. Now, this is a very general definition of a Riemann sum, which allows for any x sub I star in the ith subinterval, and it allows for unequal subinterval lengths. So once again, for any given partition p, we get a different Riemann sum for each collection of the x sub I stars selected. Here are some common Riemann sums based on the selection of x sub I star. If x sub I star is the left endpoint of each subinterval, then the sum is called a left Riemann sum, and I'll denote this as L sub n. And using the right endpoints for x sub I star, the sum can be written like this. If x sub I star is the right endpoint of each subinterval, then the sum is called the right Riemann sum, denoted R sub n. And if x sub I star is the midpoint of each subinterval, denoted x sub I bar, then the sum is called the midpoint sum, denoted M sub n. Riemann sums arise in a variety of AP calculus applications. Let me just consider a quick graphical illustration of a midpoint Riemann sum. Suppose we want to estimate the area of the region S, bounded by the graph of y equal 1 minus x squared, the x-axis and the y-axis, as shown in the figure on the left. Note that the area of this region must be between 0 and 1, because the region S is contained in a square with side of length 1. But it seems like we can certainly find a better estimate than this. Consider the partition of the interval 0 to 1 with 4 equal subintervals. In each subinterval, draw a rectangle with height equal to the value of the function at the midpoint of the subinterval, as shown in the figure. You can see that if we add the areas of these rectangles, this would be a reasonable approximation to the area of the region S. Here is the sum of those areas, where the area of each rectangle is the height times the width, or again, the value of the function at the midpoint of each subinterval times the width of the subinterval. And this is simply a midpoint Riemann sum. As an aside, there are lots of other Riemann sums we could use here to estimate the area of S. For example, you might try a left Riemann sum or a right Riemann sum. And it's not clear whether this is an underestimate or an overestimate of the real, true area of the region S. But it also seems reasonable that if we want a better estimate of the area of the region S, we should take n larger and larger, or equivalently, let n increase without bound. This type of limit of a Riemann sum, that is, as n goes to infinity, is so important in calculus that it has a special name and notation. Here's the definition of the definite integral of a function f from a to b. Suppose f is a function defined on the closed interval a to b, and p is a partition of the interval a to b, defined by these values. Choose the sample points x sub I star in the ith subinterval, and let delta x sub I be the width of the ith subinterval. The definite integral of f from a to b is denoted this way, and defined to be the limit of the Riemann sum, provided of course that the limit exists, and results in the same value for all possible choices of the sample points. Now, just a few quick notes here. This symbol is called a definite integral sign, and it's kind of like an elongated S, and that sort of makes sense because a definite integral is a limit of sums. The function f of x is called the integrand, and the values of a and b are the limits of integration. A is the lower limit and b is the upper limit. And the symbol dx indicates the independent variable is x. I really feel obligated to take a closer look at this very important definition. First, even though we do not require epsilon delta arguments or theoretical arguments about limits on the AP Calculus exam, here's a look at the precise meaning of this limit. For every epsilon greater than 0, there exists an integer capital N, such that this difference is less than epsilon for every integer small n greater than big N, and for every choice of the sample points x sub I star. It just means that we can make this sum arbitrarily close to the value of the definite integral. And here's another way to write this definition based on the description of the partition P. The norm of a partition is simply the maximum width of all of the subintervals, and it's denoted this way. So, as n increases without bound, we are dividing the interval into more and more pieces, each smaller and smaller. So the norm of the partition goes to 0. Therefore, we can also define the definite integral from a to b using the limit as the norm of the partition goes to 0. And finally, this definition says that the definite integral is the limit of a Riemann sum. So an integrable function can be approximated to within any degree of accuracy by a Riemann sum. And one more aside. At this point in the class, I really don't have a method to evaluate a definite integral. Well, except to find the limit of a Riemann sum, which as we all know can be very painful. We still need a quick, efficient way to evaluate the definite integral of f of x from a to b. And in your class, you know that this leads to antiderivatives and the fundamental theorem of calculus. So finally, let's put all of this together to solve the problem. We need 3 subintervals of equal length. So the partition is 0, 4, 8, and 12. We're computing a midpoint Riemann sum, so the midpoint of each subinterval is x sub 1 star is 2, x sub 2 star is 6, and x sub 3 star is 10. Here's the symbolic expression for the midpoint Riemann sum. I'll read the necessary values of y prime from the table, and the length of each subinterval is 4. A little simplification leaves me with a final answer of 20. Here are the scoring guidelines for this problem. Part E was worth 2 points. 1 point for the correct form of the midpoint Riemann sum, and 1 point for the final estimate. Here are some interpretations of these guidelines to help award points and to prepare for problems like this on the next AP Calculus exam. The first point is earned for a correct midpoint Riemann sum. It's kind of a conceptual or a method point. To earn this point, the student must present correct multiplication and evidence of a sum. Now, the sum can have one error and still earn this point. In this case, we think of this as the 5 out of 6 rule. There are 6 pieces to this midpoint sum, 2 in each product. If 5 of the 6 pieces are presented correctly, then the student would earn the first point, but then they're not eligible for the second. Even though we recognize that some of our students are very good at solving this type of a problem, a bald estimate of 20 does not earn any points here. The specific numerical values for y prime must also be used from the table. That is, the student cannot earn the estimate point without indicating these exact values. And finally, if any simplification is presented, it must be correct. If the student makes an error in simplification, then they do not earn the estimate point. In Part F, we need to explain the meaning of this definite integral in the context of the problem. The key concept here is displacement. Let's suppose a particle moves along a horizontal line so that its position at time t is given by s of t. Then we know that the velocity is the change in position over time. So the velocity is the derivative of s. That is, v of t is equal to s prime of t. And so, using the fundamental theorem of calculus, the definite integral of the velocity function from t sub 1 to t sub 2 is s of t sub 2 minus s of t sub 1. Look at the right side of this expression. This means that the definite integral of the velocity function is the net change in position, or the displacement of the particle over the time period from t sub 1 to t sub 2. Let's use this definition or concept of displacement to solve this problem. We know that y of t is the vertical position of the particle at time t. Now, the important point here is that the particle is moving along a line. It's a vertical line, but that doesn't change my interpretation. We know that the change in position with respect to time is velocity. So that means that y prime of t is the velocity of the particle at time t. Therefore, this definite integral represents the displacement in meters by the particle over the time interval 0 to 12 seconds. Here are the scoring guidelines for this problem. Part F was worth 2 points. 1 point for the correct interpretation, and 1 point for including the correct units as asked for in the problem. Here are some notes about these scoring guidelines. To earn this interpretation point, the student must clearly indicate the time interval, t equals 0 to t equals 12. A common error here is for students to reference a specific point in time, for example t equals 12, or to say something like after 12 seconds. So we need the time interval here. Here are some common student responses that are acceptable ways of indicating the time interval. On the time interval 0 to 12, or just interval notation. And we usually accept phrases like over or during the first 12 seconds, or even during the 12-second interval. Now, we're not looking at the units attached to time for this first point. So, frankly, the student can use any unit of time. However, if it's incorrect, they will not earn the second point. And the interpretation must include the word displacement, or the phrase change in position, or net distance traveled. Now, there are probably some other acceptable phrases, but these are the most common. Professional judgment is needed in scoring these problems for some of the more obscure presentations. And the units point is awarded for the use of the distance units, which are meters. And again, the time units are not necessary here, but if they are included, they must be correct. I hope this video gives you a good idea of how to solve these problems using the necessary AP calculus concepts, and a reasonable expectation of how they would be scored. We'll look at more parts of this free response question in the next video.